Hello there, and welcome back to the quiet corners of Sleep Drift Stories. Tonight, we invite you to settle your mind not on the noise of the day, but on the majestic, invisible architecture of the sky above us. We are going to drift through the atmosphere, exploring the deep science and the profound paradoxes of the weather, the vast, breathing system that cradles our world. Before your eyelids grow heavy and your thoughts begin to blur, take a long, slow breath. Let the world outside recede and simply allow your attention to settle on the gentle whisper of the wind, the soft murmur of distant thunder, or the silent glide of a distant, colossal cloud. We are about to uncover secrets of the air that challenge everything you thought you knew about gravity. Heat and the quiet dance of molecules. The sky, which we so often regard as an empty canvas of blue or gray, is in fact the planet's most dynamic and least understood ocean. It is a constantly circulating envelope of gases, energies, and suspended water. And in its workings, we find some of the most beautiful and counterintuitive truths of existence. Our journey begins high above the ground with a question that seems absurd on its face, yet holds a profound answer. If a cloud looks like a handful of cotton candy, how much does it actually weigh? The answer, perhaps, is the perfect starting point for sleep, because it asks you to hold two contradictory ideas in your mind at once: weightlessness and staggering, unimaginable mass. When you look up at a fluffy, white cumulus cloud, the kind that sails lazily across a summer day, casting gentle shadows on the fields below, it appears to be made of nothing but spun sugar, soft cotton, or condensed breath. It is the epitome of ethereal buoyancy, a thing of pure form, floating in a vast blue void. And yet, this soft, seemingly weightless entity carries within it a weight that defies common sense, an immense, sinking mass equivalent to over 1 million fully grown African elephants. We're not talking about the large, menacing thunderheads yet. We are discussing a typical, fair-weather cumulus cloud, and it can contain hundreds of thousands of tons of water. This is not hyperbole. It is a measurable scientific reality. A typical 1 cubic kilometer cumulus cloud, though its edges look feathered and delicate, can contain enough condensed water to fill dozens of massive tanker ships or a small reservoir. The sheer scale of this water mass, trapped yet airborne, invites a moment of genuine awe. Think of the paradox. How can something so immensely heavy appear so delicate and remain suspended against the relentless pull of gravity? The atmosphere manages this magnificent balancing act through a concept called the microscale, the unseen dimension where physics plays a different game. The water is not gathered into a cohesive, heavy block. Instead, it is distributed into billions upon billions of microscopic droplets, each typically less than 10 micrometers in diameter, smaller than the width of a human hair. These tiny droplets are so minute that they are subjected to air resistance far more than to gravity. They are simply too small to gain the momentum needed to fall rapidly. And the ultimate reason they are kept aloft, defying the elephantine weight they collectively represent, is the updraft invisible. Rising currents of warm air generated by solar heating of the Earth's surface. This warm air, being lighter than the surrounding cooler air, acts as a constant, gentle elevator, pushing the tiny droplets upward faster than gravity can pull them down. The cloud, then, is not a static formation. It is a constant, churning battleground, where the power of the sun and the resistance of the air win, moment by moment, against the enormous downward pull of gravity. As you settle deeper into your pillow, imagine the atmosphere as a gigantic, silent engine lifting the weight of lakes and reservoirs back into the sky, constantly recycling the water that sustains every living thing on the surface below. This paradox of delicate strength and immense scale is a theme we will encounter again and again in the science of weather. A theme that assures us that the most peaceful things in nature often conceal the most profound forces. It is the silent, profound weight of the sky, floating just out of reach, yet held together by principles we barely perceive. We transition now from the soft, suspended water of the cloud to another, much more violent paradox, the lightning. If a cloud represents immense, contained weight, then lightning represents immense, contained energy. It is a brief, jagged scar across the night sky, a flash that lasts mere milliseconds. Yet, in that single, searing instant, a lightning bolt contains more energy and heat than we can truly fathom. It is a common fact, but one always worth dwelling on as we settle into rest. A lightning strike can reach a temperature of over 30,000 degrees Celsius, about 54,000 degrees Fahrenheit. To put this astronomical figure into a relatable, quiet perspective, let's look far beyond our planet, the visible surface of our sun, the blazing orb of creation and life, burns at about 500 degrees Celsius. Lightning is therefore several times hotter than the fiery face of our solar parent, compressed into a pencil-thin channel of air that splits the sky a few miles above your head. This comparison is astonishing. The most extreme heat in our solar system's largest body is somehow replicated in a brief, atmospheric flicker right here on Earth. This immense heat is generated by the rapid, violent movement of electrons, essentially creating a momentary terrestrial sunbeam. What we are witnessing in a lightning strike is the raw, untamed power of the atmosphere balancing itself out. The clouds, those colossal reservoirs we just discussed, build up immense electrical charge. Separation, positive charges. Being slightly lighter, tend to rise. while negative charges settle near the bottom. When the difference in potential between the negative charge at the cloud base and the positive charge on the ground becomes too great, the atmosphere, which is normally an excellent insulator, can no longer hold the energy back. It finds the path of least resistance, initiating a process called the stepped leader, a nearly invisible, tentative channel of charge seeking the ground in rapid sequential steps. When this leader connects with the upward surge of positive charge, the brilliant, visible return stroke, the main discharge occurs. That is the blinding flash. The sudden, violent release of energy that superheats the air around it. The air molecules, violently and instantaneously ionized, turn into a brilliant column of plasma, a highly energetic state of matter that glows with blinding light and heat. This incomprehensible burst of heat has a powerful secondary consequence, which is the familiar, comforting, deep rumble of thunder. When the air along the lightning channel is heated to such an extreme temperature in less than 1,000th of a second, it expands with explosive force. This expansion is so rapid that it generates a powerful shock wave, a true explosion of the atmosphere. As this shock wave travels outward and dissipates, we perceive it as the low, rolling drumbeat of the storm. The distinct sound, whether a sharp crack or a deep rumble, depends entirely on your distance from the bolt and the way the sound reflects off the terrain. Because light travels so much faster than sound, we always see the flash first, giving us a moment of silent anticipation before the noise reaches us. This lag is why counting the seconds between the two can precisely reveal how far away the storm is, approximately 5 seconds per mile. But lightning is not merely destructive, it is profoundly creative, performing a crucial task for all terrestrial life. The nitrogen gas that makes up nearly 78% of our atmosphere is essential for plant life. Yet, in its gaseous form, it is chemically inert, unavailable for absorption by roots. The immense heat and pressure of lightning is one of nature's primary ways of fixing that nitrogen, splitting the incredibly strong nitrogen molecule and combining it with oxygen to create nitrates and nitrites. These compounds are then dissolved and washed down by the rain, acting as a natural, massive fertilizer for the ground. So, in every flash, the sky is not just making noise and light, it is enriching the soil, seeding the next generation of crops, trees, and flowers. The storm is a paradox of both life and fury. Now, let us listen to the gentle fading of the thunder, knowing that in its wake, the quiet earth is made richer, and the atmosphere has completed a fundamental task of planetary sustenance. We leave the thunder and its hidden fertility now, and turn our attention to the simple, pervasive act of rain falling. It's an image so deeply embedded in our collective consciousness, the sad, beautiful image of the teardrop. We see it in cartoons, in children's drawings, in stylized graphics, a perfect, pointed top leading a rounded bottom, a shape we associate with sorrow, or perhaps the rush of speed. But the actual shape of a falling raindrop tells a far more nuanced and strangely humbling story of atmospheric physics, a story of resistance and aerodynamic balance. To truly understand rain, we must discard the teardrop entirely. The reality is that the smallest drops, those that form in gentle mist or drizzle, are nearly perfect spheres, held together by the elegant, invisible force of surface tension, the same force that allows a mosquito to walk on the surface of a pond without breaking the water's delicate skin. As the drops gather more water and grow larger, they begin their rapid descent through the atmosphere. And this is where the air resistance comes into play. The sheer velocity of the fall, combined with the pressure of the air pushing up from below, flattens the bottom of the spherical drop. If you could capture a mid-sized raindrop in a high-speed photograph, you wouldn't see a teardrop. You'd see something far more humble and less dramatic a shape that resembles a tiny, translucent hamburger bun, or perhaps a slightly deflated hot air balloon. The largest raindrops, those that contribute to a heavy downpour, are often stretched so wide that they become structurally unstable, sometimes taking on a horseshoe or parachute-like appearance before the air resistance overwhelms the surface tension, causing them to fragment into smaller, more manageable droplets, a beautiful, dynamic form of self-regulation that prevents single, massive drops from plummeting to the ground. This image of the falling hamburger bun drop is a quiet invitation to see the world not as we imagine it, but as it truly is, governed by subtle, elegant mechanics. It's a reminder that beauty in nature is often found in the most functional and surprising geometries, a perfect harmony between gravity pulling down and air resistance pushing up. The illusion of the teardrop is a trick of perspective. It's what happens to water after it lands, as gravity pulls it along a window pane or a cheek, stretching the liquid out as it slides. But the drops themselves, tumbling in their silent millions from the colossal weight of the clouds above, hold their own unique, rounded perfection. And once those beautifully shaped drops touch the ground, they release one of the most comforting and evocative scents in the natural world: the smell of petrichor. The fragrance that rises from dry soil just after the first drops of a rain shower is not simply the scent of wet dirt. It is a complex, ancient cocktail of chemistry and biology, and there is indeed a scientific name for it, derived from the Greek petra, meaning stone, and ichor, the golden fluid that flowed in the veins of the Greek gods. Petrichor has a minimum of 3 main components, each playing a critical role in the final, intoxicating bouquet. First, there are oils secreted by certain plants, released during long, dry spells and absorbed into the clay and rocks of the soil. The rain acts as a catalyst, splashing these oils out of their hiding places and aerosolizing them into the air. Second, and perhaps most earthy in its aroma, is geosmin, a compound produced by a common soil bacterium called Streptomyces. This microbe thrives in dry conditions and releases geosmin as a metabolic byproduct. To us, it smells rich, earthy, and profound, the quintessential smell of soil. Some studies even suggest our human noses are incredibly sensitive to geosmin, capable of detecting it at parts per trillion. Perhaps because our deep biological history is tied to following the scent of rain for survival. Finally, during intense storms, a sharp, clean note is often added by ozone, created when lightning's electrical charge splits atmospheric oxygen molecules. The resulting clean, fresh scent of ozone blends with the earthy geosmin and plant oils, creating the unforgettable, reassuring fragrance of a world being quenched. When you breathe in petrichor, you are inhaling a story that links plant, microbe, stone, and sky, a story that feels as timeless and deep as the earth itself, a fragrant promise of renewal. We ascend once more, leaving the sense of the soil behind to consider another form of descending beauty, the snowflake. We hold a quiet, romantic image of snowflakes, each one a six-pointed star, descending in a slow, uniform, almost choreographed ballet. While the geometry of the ice crystal is indeed one of the great marvels of physics, a testament to the H2O molecule's ability to lock together in precise, elegant angles, their descent is anything but uniform. The speed at which snowflakes fall can vary tremendously, a quiet dance of air resistance and mass that makes every journey unique, a testament to chaos theory applied to ice. A small, single ice crystal, delicate and barely visible, what meteorologists might call a diamond dust particle, may drift down at a pace so slow it seems to be hovering, reluctant to leave the sky, perhaps descending at a fraction of a meter per second. Conversely, a large, heavy aggregate, a collection of many smaller crystals that have collided and stuck together, forming a macroscopic flake, can tumble earthward at speeds several meters per second, falling significantly faster. These larger, clumpy flakes are responsible for the thick, fast accumulations we call heavy snow, where the ground is covered rapidly. The atmosphere is like a complex ballroom, and the snow is a party where some dancers are executing slow, graceful glides, while others are caught up in a much more rapid, headlong spin towards the earth. This variation in speed is compounded by wind shear and atmospheric turbulence, which complicates the trajectory, often carrying flakes sideways or even temporarily upwards before gravity inevitably wins. The journey of a single snowflake from its birth, high in the cloud, to its gentle rest on a windowsill can be many miles long. A silent, erratic voyage shaped by every invisible current it encounters. Knowing this, when you next watch a snowfall, try to see it not as a single blanket descending, but as billions of individual, complex journeys, each one following a unique, chaotic, and beautiful path dictated by microclimates and subtle wind currents. And speaking of size, while we generally think of snow in small, delicate terms, the sky, under the right rare conditions, can produce giants. The necessary conditions are a specific combination of high moisture content to provide ample building material, temperature just below freezing, which makes the crystals sticky, and calm winds to prevent them from shattering during aggregation. When these factors align, flakes can collide and stick to one another en masse, creating spectacular composite structures. The most famous extreme report is from Fort Keogh, Montana, in 1887, claiming snowflakes of an almost mythical scale, 15 inches across, larger than an average dinner plate. While many experts view this specific measurement skeptically, perhaps attributing it to compacted snow rather than a single frozen structure, we know from reliable modern records that flakes the size of a U.S. half-dollar coin over an inch wide are certainly possible. The very idea that such immense frozen plumes can drift from the heavens adds a necessary, quiet magic to the deep winter night. From the gentle drift of snow, we move to the storm's furious manifestation, the blizzard. A blizzard is far more than just a heavy snowstorm. It is a specific, violent synergy where high winds over 35 mph and falling or blowing snow combine to create a critical lack of visibility, often dropping to less than a quarter mile for hours on end, all while temperatures and wind chills reach dangerous lows. The key defining characteristic of a blizzard is the whiteout, a profound condition where the entire world seems to vanish, merging into a single, swirling color. In the midst of a full whiteout, all sense of horizon, ground, and sky disappears into a swirling, monochromatic chaos. This is why travelers caught in them, particularly in open plains or mountainous regions, have described the frightening sensation of being unable to see their own hand held a few feet in front of their face. The snow is no longer falling from the sky. It is being violently whipped up by the wind, transforming the atmosphere into a blinding, abrasive wall of ice crystals. This disorientation is not just inconvenient, it's profoundly dangerous, capable of quickly leading to lost bearings, panic, and rapid hypothermia. The wind chill factor, the rapid removal of heat from exposed skin by the moving air, becomes the true killer in these conditions. Freezing skin in minutes. The blizzard represents the atmosphere at its most powerful and disorienting. A complete erasure of familiar reality. And yet, when the storm finally passes, that chaotic energy leaves behind a world of profound, almost religious silence. The landscape muffled and transformed by a thick, seamless blanket of white. It's a reminder that extreme weather is a powerful, temporary sculptor of our world, capable of simultaneously inducing panic and, in its aftermath, total, absolute calm, the kind of silence that's perfect for letting the mind finally rest. Now, leaving the chaotic silence of the whiteout, let's consider a different form of precipitation, one that builds its history layer by layer, like a geological record of the storm hailstones. These icy missiles form in the heart of powerful, towering cumulonimbus storm clouds, particularly those associated with supercells, which have extremely strong, persistent updrafts. These updrafts, the same gentle currents that held those million-elephant clouds aloft, become violent elevators in a severe thunderstorm, lifting ordinary raindrops high into the freezing zone of the atmosphere, where they instantly freeze into small pellets of ice, becoming the nuclei of future hailstones. Here's the fascinating part, which speaks to the incredible dynamics within a mature storm cloud. The hailstones do not fall immediately after freezing. They may be caught in the intense, cyclical circulation of the supercell, falling through the cloud, collecting a layer of supercooled water that is still liquid even below its freezing point, and then being violently carried back up by the strong updraft. When they rise again into the higher, colder altitudes, that collected liquid water instantly freezes, forming a new, distinctive layer of ice. This cycle can repeat dozens of times. By the time a large hailstone finally overcomes the updraft's immense power and plummets to Earth, if you were to slice it open, you would find a cross-section of concentric rings, much like the annual growth rings of a tree or the layers of an onion. Each layer is a record, an icy diary detailing a single vertical journey through the storm's churning interior. Meteorologists can analyze these layers to determine how many times the hailstone was lifted and frozen anew, essentially mapping the severity and longevity of the storm that created it. The distinction between layers clear ice forming when the water collects slowly and freezes as a sheet, and opaque ice forming when the water freezes instantly and traps tiny air bubbles is a silent history of atmospheric turmoil. Most hailstones are indeed pea-sized and harmless, but the violent, repeated cycles in a severe supercell can create true monsters. The most astonishing recorded example occurred in Vivian, South Dakota, in 2010. The hailstone that fell there was nearly the size of a volleyball, measuring 8 inches 20 centimeters in diameter and weighing nearly 2 pounds, 2.9 kilos. Imagine an ice sphere of that magnitude, forged in the violent heart of the sky, hurtling towards the ground at terminal velocity. Hail is a pure, solid example of the atmosphere's most turbulent forces translated into a physical, frozen form, a natural sculpture. Dangerous and beautiful, capturing the memory of the storm in its very design. We shift abruptly from the structured ice of hail to a force that is the very definition of concentrated fury, the tornado. These twisting funnels of wind are perhaps the most visually terrifying weather phenomenon, and their power often seems to defy the known rules of physics and material science. One of the strangest, yet verifiable, pieces of evidence attesting to this extreme power is the fact that in a major tornado, lightweight, delicate objects, specifically pieces of straw, can be accelerated to such a velocity that they are driven straight through solid wood. This is not a tall tale of folklore or an optical illusion. It's a documented effect of extreme wind speed and focused kinetic energy. The tornado's vortex is capable of accelerating debris to speeds that can exceed 200 miles per hour, 320 km/h. When a simple blade of grass or a piece of straw hits a stationary object, like a wooden fence post or utility pole, at that kind of velocity, it acts less like soft plant material and more like a stiff, piercing projectile, concentrating all its modest mass and momentum into a tiny point, the surrounding wood, unable to absorb the energy quickly enough, parts momentarily, allowing the straw to embed itself. It's a vivid, unsettling illustration of how the sheer speed and focused nature of the air, when organized into a vortex, can fundamentally alter the perceived properties of matter, transforming the fragile into the destructive. The wind essentially provides the hammer, turning the most insignificant objects into high-velocity projectiles, and the intensity of the winds inside a tornado are quite literally comparable to the speed of modern travel. The most severe tornadoes, categorized as EF5 enhanced Fujita scale, can contain rotational winds that have been measured at over 300 miles per hour, 480 km/h. This speed is comparable to the cruising speed of a large commercial passenger jet. At these velocities, the forces unleashed are astronomical. Whole houses are swept clean from their foundations. Asphalt is scoured from roads, and heavy objects like cars and steel beams can be tossed like children's toys. Storm chasers who have survived close encounters universally describe the sound of an EF5 not as wind, but as the overwhelming, constant, deafening roar of a freight train bearing directly down upon them, often accompanied by a pressure drop so extreme it feels as if your eardrums are being violently pulled outward. A tornado is the planet's atmospheric fury distilled into its most concentrated, destructive column, a humbling reminder that the air we breathe can, in an instant, move with unimaginable, reality-bending force. If the tornado is concentrated fury, the hurricane is fury on a continental scale, a storm so vast it spans hundreds of miles and lasts for days or weeks. This immense, spinning engine, known scientifically as a tropical cyclone, is fueled entirely by the warm, moist air rising from tropical oceans, the fuel being the latent heat released when water vapor condenses into liquid cloud droplets. This process of condensation drives the entire colossal system, making the hurricane a machine of almost incomprehensible power. To grasp the true scale of this energy, consider a fact that should humble any human endeavor: the amount of energy released by a mature hurricane in just a single day is greater than the total energy output of every single power plant on Earth combined. Imagine every coal, nuclear, hydroelectric, wind turbine, and solar farm across the globe running at peak capacity, and they still fall short of the natural thermodynamic engine of a single large storm spinning over the sea. This energy, primarily released as latent heat, is constantly drawn from the warm ocean waters, allowing the storm to perpetuate itself until it hits cooler water or land. It is Earth's most spectacular weather machine, a truly humbling display of atmospheric thermodynamics. The process is a spectacular feedback loop. Warm, moist air rises, condensation occurs, releasing massive amounts of heat. This heat warms the air, causing it to rise even faster and drawing in more air from the surface, increasing the wind speed and drawing in more moisture, thus strengthening the storm. This continuous cycle means the hurricane is not just powerful, it is fundamentally self-sustaining as long as its fuel source, warm ocean water, is available. And yet, nestled at the very center of all this chaos is one of the weather's strangest and most unsettling phenomena: the eye. If you manage to survive the howling, destructive winds, and torrential rain of the storm's eye wall, the surrounding, most violent ring of towering thunderstorms, you are suddenly met with a zone of eerie, almost unbelievable calm. The eye is a circular region, often 20 to 40 miles wide, where the clouds part, the winds drop significantly often to a dead calm, the rain stops, and sometimes the sun even shines down from a perfectly clear sky above. It is the literal, still center of the storm's rotational vortex. This phenomenon occurs because the air in the center, having risen so high and lost its moisture, is forced to sink back down. This sinking air warms and dries as it descends, suppressing cloud formation and creating the clear, tranquil space at the heart of the monster. It is a moment of profound, unsettling peace, like being in the center of a gigantic, spinning potter's wheel, but it is a deeply deceptive peace, filled with dread, because those within the eye know that the silence is temporary, and that in a short time, the other side of the eye wall, the second half of the storm, will return with full, devastating force. For coastal communities, the passage of the eye can sometimes trick residents into believing the storm has passed, only for them to be caught completely off guard by the returning fury. This moment of false safety is perhaps the most profound atmospheric metaphor, even at the heart of total chaos. There can be a fleeting, strange, but inevitable moment of deceptive stillness. The weather's power is often measured not just in violent, concentrated storms, but in vast, seasonal transformations that shape entire continents, cultures, and landscapes. Few phenomena illustrate this profound, rhythmic power better than the monsoon. A monsoon is fundamentally a major, sustained seasonal shift in the prevailing wind direction over a large region, causing a dramatic and prolonged change in precipitation, often swinging from extreme dryness to extreme wetness. For months, a land may lie utterly parched, the earth baked, dry, and cracked, waiting in strained anticipation for the shift. Then, as the immense pressure and temperature gradients of the continent reverse, the winds shift, often bringing massive influxes of moisture from the tropical ocean, and the skies open. The landscape is utterly, completely transformed, often within days. These rains are both life-giving and destructive in equal measure. They are the essential source of water for crops that feed hundreds of millions of people across India, Southeast Asia, and parts of Africa, dictating the entire rhythm of planting, harvesting, and cultural life. Farmers' calendars are built around the timing of the monsoon's arrival, and festivals often celebrate its life-bringing torrents, but they also bring with them the constant threat of catastrophic flooding and landslides, reshaping river systems and coasts with immense geological power. The sudden, sustained volume of water can scour away topsoil, overwhelm infrastructure, and completely redraw temporary boundaries of waterways. To witness the arrival of the monsoon is to see weather operating on a continental scale, an atmospheric turning point so vast and predictable it changes the face of nations, turning arid lands into shimmering seas of green and swelling rivers until they roar with temporary life. It is a slow, rhythmic, predictable surge of atmospheric power that binds the human story to the pulse of the planet itself. This predictable, seasonal flood stands in stark contrast to one of the most extreme geographical paradoxes on Earth, the profound, silent aridity of the Atacama Desert in Chile. It is known as the driest non-polar desert in the world, a vast, silent expanse of rock and sand that is so devoid of water that NASA studies its soil as a genuine analog for the surface of Mars. In many parts of the Atacama, meteorological records show that no measurable rain has ever fallen, and some regions are believed to have gone decades, sometimes even centuries, without a significant drop of precipitation. The incredible aridity is created by a potent combination of geography and oceanography. The towering Andes Mountains block virtually all moisture from the Amazon basin to the east, and the cold Humboldt Current in the Pacific creates atmospheric stability and fog, which prevents the formation of the large, unstable rain clouds from the west. Yet, even in this extreme, profound dryness, life holds on in ingenious and specialized ways. Certain highly adapted plants, known as phreatophytes, survive by drawing deep moisture from far below the surface, or more commonly, by collecting moisture from the dense coastal fog called Comanche that drifts inland. Microscopic organisms, adapted to this harsh environment, cling to existence deep in the soil or within salt deposits. And on those rare, truly miraculous occasions, a phenomenon that may happen only once every 5 to 10 years, when a significant rain does manage to breach the atmospheric barriers, the desert explodes into a spectacular, sudden bloom called the Desierto Florido Flowering Desert, where the dormant seeds of countless wildflowers burst into life, carpeting the barren landscape with ephemeral, brilliant color for a few short weeks. The Atacama is a testament to the fact that weather's influence is not uniform. It's a profound silence where the absence of rain is as powerful as the monsoon's torrent. And every single drop of water is a miracle of survival. It is the silence of an atmosphere that has almost ceased to participate in the water cycle. Now, having visited the world's driest place, where the sky barely yields a drop, we must pivot to its antithesis, the wettest inhabited spot on Earth, the village of Mawsynram in northeastern India. Here, the amount of rainfall is astonishing, averaging nearly 12 meters, 39 feet per year. To visualize this extreme, non-stop deluge that is a vertical wall of water, taller than a 4-story building, pouring down annually, a volume that defies typical human experience with precipitation. The key to this incredible, relentless downpour is a specific and dramatic geographical funnel. The summer monsoon winds from the Bay of Bengal carry immense amounts of moisture inland. When this moisture-laden air hits the Khasi Hills, it is forced to rise sharply. As the air mass gains altitude, it cools rapidly, causing immense, almost perpetual condensation, and the resulting torrential, record-breaking rainfall. The location of Mawsynram, nestled right on the side of this mountain range, receives the full, concentrated force of this orographic lift. Life in Mawsynram is entirely shaped by this extreme, constant precipitation. Villagers must build their homes with extremely sturdy roofs, often weighted down with rocks or thick thatch, to withstand the relentless pounding and prevent leaks. They have also developed ingenious methods to cope with the swollen rivers, most famously by weaving together the living aerial roots of rubber trees to create natural, strong bridges that can withstand the perpetual deluge. Where most of the world measures rainfall in inches or centimeters, in Mawsynram, they measure it in towering, annual walls of water that shape culture, architecture, and daily rhythm. It is a place of endless, roaring water, perfect for the mind to drift into. Safe and dry in the knowledge that such an extreme environment is being peacefully observed from afar, from the soaking, verdant hills of Mazenram. We move to the absolute extremes of temperature, beginning with the searing, deadly heat. The official hottest air temperature reliably recorded on Earth was measured in Furnace Creek, Death Valley, California. In July 1913, a furnace-like 56.7 degrees Celsius, 134 degrees Fahrenheit. This is not simply hot weather. This is a survival-threatening, thermal extreme where the air itself feels like a physical barrier. At this temperature, the sheer heat stress pushes the human body to its absolute limit, struggling to shed warmth into an environment that is hotter than the body itself. Asphalt softens. Exposed metal can cause third-degree burns on contact, and car tires risk melting under extended use. Death Valley is a deep, narrow basin far below sea level, a geological trap where air is forced to sink and compress, heating it intensely. This heat is then trapped by the surrounding mountains and the arid, dark soil, which absorbs and re-radiates the sun's energy. Further amplifies the effect. This heat rises off the rocks and sand in shimmering waves, distorting the view and creating a visual representation of the intense thermal energy. The fact that temperatures can reach such a blazing furnace on our own planet is a stark reminder that the atmosphere can turn from a gentle envelope into a hostile, deadly environment, an environment of severe energy concentration. The opposite thermal extreme is no less alien and unforgiving than the heat of Death Valley. Journeying now to the high plateau of the interior of Antarctica, far from the moderating influence of the sea and high above sea level, we find the core of Earth's deepest cold. At the Russian-operated Vostok station in 1983, scientists recorded the planet's official lowest air temperature, a staggering 89.2 degrees Celsius, or 128.6 degrees Fahrenheit. This measurement occurred during the deep, sunless polar winter. More recently, satellite data has even measured pockets of air in nearby hollows dropping to nearly 98 degrees Celsius under the most pristine, clear sky conditions, where heat can radiate straight into space without obstruction. This is cold that transcends the familiar. It is colder than dry ice solid carbon dioxide, and colder than the average surface temperature of Mars, which is around 62 degrees C. In this environment, the very nature of matter changes. Steel becomes brittle and prone to shattering. Liquid gases freeze, and the air is so thin and dry that breath instantly freezes into a fine, sparkling mist of ice crystals. Exposed skin can suffer severe frostbite and freeze solid almost instantly. This is the ultimate frontier of cold on our planet, where the air itself feels almost solid and crystalline. And human survival is possible only through extraordinary engineering. Complex insulation systems, and constant, diligent vigilance. This cold is created by the combination of extreme altitude, distance from the sea, and the intense thermal radiation from the surface into the clear, dry air. It is a world of deep, profound, almost unbearable silence, occasionally broken only by the thin, high-pitched howl of the frozen wind. It is a place where the atmosphere meets its most stoic, crystalline extreme, a perfect, silent backdrop for the mind to find its own stillness, knowing that such profound, frozen energy exists. We now transition from the visible, dramatic extremes of temperature, the sun's heat, versus the polar night's cold, to acknowledge a danger that is far quieter, more subtle, yet statistically the most lethal form of weather: the heat wave. While tornadoes, hurricanes, and floods make dramatic, immediate headlines, their victims are often fewer than those claimed silently, insidiously, by prolonged periods of excessive heat and humidity. Heat waves kill more people globally than any other single category of weather event combined. The danger of a heat wave lies in its duration and its relentless effect on the human body, particularly in densely populated areas. When temperatures soar for days or even weeks with little or no reduction in temperature at night, the body struggles relentlessly to maintain its core temperature of approximately 37.5 Celsius. This sustained heat stress puts an enormous, often fatal, strain on the heart and circulatory system, leading to heat stroke, dehydration, and organ failure, especially in vulnerable populations. Cities are particularly susceptible, becoming urban heat islands where concrete, asphalt, and dark roofing materials absorb massive amounts of solar radiation during the day, releasing it slowly at night, creating suffocating conditions with no thermal respite. The heat wave is an invisible threat. There is no wind, no crashing rain, and no visible damage until the stress manifests in rising hospital admissions, withered crops, and stressed ecosystems. It is weather's most insidious threat, not arriving with a roar or a flood, but creeping in quietly, turning the surrounding atmosphere into a subtle, deadly pressure cooker. The quiet consistency of the elevated temperature is what overwhelms life, making it a powerful lesson in the cumulative impact of even subtle environmental stress. We transition now from the searing, invisible threat of the heat wave to the quiet mystery and beautiful disorientation of fog. Fog is essentially a cloud that has settled down to meet the ground, but its effects on our perception of the world can be utterly transformative, wrapping the landscape in a profound, pale silence. While often beautiful, blurring trees and buildings into ghostly, ethereal shapes, fog can become so dense that it reduces visibility to just a few feet. The key scientific difference between fog and a cloud lies in its formation altitude, but the physical process is the same. The air is cooled to its dew point, causing airborne water vapor to condense into billions of minute liquid droplets suspended near the surface. People walking through a particularly thick pea-soup fog have described the unsettling sensation of being unable to clearly see their own feet beneath them, as the light from above is completely scattered by the dense blanket of suspended water. In this condition of near-zero visibility, sound also behaves strangely. It is often described as being muffled and close, as if the air itself is thick and heavy, absorbing the high frequencies. Conversely, sound signals like foghorns or warning bells can sometimes travel vast distances in specific thermal inversions above the fog layer, causing odd auditory illusions. Ships slow to a crawl, flights are grounded, and the familiar world disappears, replaced by a temporary landscape that feels otherworldly, like moving through a dream where the edges of reality have dissolved into whiteness. Despite its soft appearance, dense fog is one of the most dangerous weather events for travel, particularly in shipping and aviation. But for the mind that seeks rest, it offers a strange, welcome form of isolation, a quiet, pearlescent barrier between you and the rest of the world. And in the silence of many deserts, where fog is rare and rain is a miracle, there is a quiet, nightly savior that sustains life dew. In the great silence of arid lands, as the sun sets, the clear air allows the ground to cool very quickly through the process of radiational cooling. When the ground's temperature drops below the local dew point, the atmospheric moisture water vapor, always present in the air, condenses directly onto rocks, leaves, and the smallest grains of sand. Each morning, the desert wakes not to rain, but to a delicate, shimmering collection of tiny beads of water. For the unique life forms of the desert, this dew is life-sustaining, an essential bridging mechanism between scarce rainfall. Organisms have evolved incredible, specialized techniques to harvest at certain darkling beetles in the Namib Desert. For instance, climb dunes and tilt their bodies into the moist night wind, causing the collected dew droplets to condense and guide the water directly into their mouths. Specific desert plants have adapted their stems and leaves to channel the dew towards their roots. Though each droplet is minute, their collective total can provide the sustenance needed to bridge the long, dry periods between rainfalls. Dew is, in essence, desert rain delivered in whispers, a quiet, reliable miracle of condensation that ensures the subtle continuity of life in the most challenging and thermally extreme environments. It is a testament to the fact that the atmosphere's most life-giving water can arrive not from a raging cloud, but from a gentle, silent thermal transaction at the Earth's surface. The cold is a masterful silent artist, capable of transforming the ordinary into breathtaking, fragile structures. On a typical winter morning, we often see frost creating delicate, fern-like patterns on windows. This is the result of water vapor condensing and freezing onto a surface. But in specific, extreme atmospheric conditions, ice can form something far more spectacular and three-dimensional hoarfrost. This phenomenon occurs most dramatically on mountain peaks, high plains, and polar regions when water vapor in extremely cold, relatively calm air freezes directly onto a cold surface, bypassing the liquid stage entirely, a process called deposition or sublimation. Crucially, this happens when the surface temperature is lower than the dew point of the surrounding air, but there is no liquid precipitation. The resulting crystals don't just form flat patterns, they stretch outward and upward into jagged three-dimensional structures. These can grow into dense, crystalline growths that resemble spiky, fragile forests of ice, with individual spears sometimes inches long. Hoarfrost transforms the entire landscape, making every twig, fence post, and surface bristle with frozen, translucent blades that catch the morning light like glass sculptures. It is a stunning display of molecular geometry made visible, a landscape of sharp, frozen silence, where a simple touch would shatter the delicate, temporary architecture that cold air and the sublimation of water vapor have created. Its formation requires stillness and profound cold, creating a temporary world of crystal silence. Contrast this quiet artistry with the deceptive, glass-like danger of the ice storm, a phenomenon often beautiful but instantly hazardous. An ice storm, sometimes referred to as a glaze event, occurs when liquid rain falls through a layer of sub-freezing air near the ground. The raindrops become supercooled liquid. They remain in liquid form, even though their temperature is below the freezing point of water, 0 degrees C or 32 Celsius F. The critical difference is that the moment these supercooled drops strike any surface roads, power lines, tree branches, cars, they instantly freeze into a solid, clear layer of ice. The result is a world suddenly encased in a dangerous, glassy shell, known as glaze ice. The danger of glaze ice is its immense density and weight. Tree branches and power lines, which can support the weight of normal snow, quickly snap under the sudden, immense accumulation of solid ice, often accumulating the equivalent weight of a fully grown person per foot of cable or branch. Roads become sheets of nearly invisible black ice, and power lines sag, leading to widespread outages that can cripple cities for days. The landscape, shimmering under streetlights, is breathtakingly beautiful, a world turned to crystal. But the beauty is edged with immediate peril. The ice storm is weather at its most deceptive, a dazzling, frozen world that is silently, constantly treacherous. reminding us that even the most beautiful weather event can carry profound infrastructural danger. The weight of ice can be immense. 1 cubic meter of solid ice weighs nearly 920 kilograms, and when that forms on every exposed surface, the structural consequences are devastating. We turn our attention back to localized vortexes of air, but this time under clear, hot skies on a dry, sunny day, particularly over deserts or plowed fields. The ground can heat up unevenly, sending a column of very warm, light air rapidly spiraling upward. This phenomenon, which represents a small-scale, fair-weather version of a tornado, is called a dust devil, or sometimes a sand pillar. Unlike tornadoes, which are born from massive, towering thunderstorms with rotation initiated miles high, dust devils form from the ground up, under calm, fair-weather conditions, born purely from thermal differences. The process is one of simple thermal convection. A patch of ground heats faster than the area immediately surrounding it. The resulting column of superheated air rapidly rises, creating a buoyant chimney. If a small, natural wind shear is present, it imparts a tiny rotational force to the rising column. As the air rises, it stretches the column vertically, which, due to the principle of conservation of angular momentum, the same principle that makes an ice skater spin faster when they pull their arms in, intensifies the rotation. This rotation then sucks up dust and debris from the surface, making the vortex visible. Many dust devils are small, harmless whirlwinds that simply flick leaves and sand a few feet into the air, but they can grow to astonishing, almost temporary skyscraper-like heights. Pilots and desert observers have reported seeing massive dust devils that tower hundreds or even thousands of feet above the ground. While they lack the destructive rotational power of a true tornado, rarely reaching wind speeds over 70 text, the largest ones can still topple sheds, break lightweight structures, lift debris, and briefly swirl with surprising violence. They are brief, chaotic, and mesmerizing miniature whirlwinds that make the normally invisible currents of heat and air suddenly, dramatically visible, a perfect example of atmospheric energy dancing across the land. They are essentially a thermal chimney twisting itself into motion. This brings us to a phenomenon similar to the dust devil, but formed over the sea, the waterspout. A waterspout is essentially a non-supercell tornado that forms over a body of water, a lake, a bay, or the open ocean. They appear as slender, twisting columns that drop from the base of a cloud, stretching down to the water's surface, acting as a visual ladder connecting the two elements. They come in two primary forms: tornadic waterspouts, which are actual tornadoes that form over land and move out over water, and the more common fair-weather waterspouts, which form directly over water. Much like dust devils, through rising thermal convection and subsequent rotation, Crucially, they are not, contrary to historical lore and popular belief, sucking up the water. Instead, the column is a condensation funnel formed by the rapid drop in air pressure within the spinning vortex. This pressure drop causes the surrounding air to cool to its dew point, forming a visible cloud column. The misty appearance at the base is mostly a dense cloud of sea spray lifted by the intense surface winds, which can be thrown many feet into the air by the vortex's rotation. Some waterspouts are weak and short-lived, spinning harmlessly before dissipating. Others are powerful enough to pose a significant threat to boaters, capable of tossing smaller vessels and snapping masts for centuries. Sailors have told tales of these towering, ghostly funnels on the horizon. From a distance, they possess a strange, silver beauty, a spiral of mist connecting the sea to the sky. They are a powerful reminder that the fury of a vortex is not confined to the land. Even the calm, open water can suddenly twist into a whirling column, reaching for the clouds above. A stunning example of how instability in the atmospheric boundary layer manifests itself. We move now to consider one of the most short-lived, yet catastrophically dangerous weather events, particularly for aviation, the microburst. A microburst occurs when a strong, mature thunderstorm suddenly and violently dumps a massive column of cold, dense air toward the ground. Unlike a vortex, like a tornado or waterspout, which is rotational, a microburst is a powerful, localized, straight line, vertical downdraft. When this column of rapidly descending air slams into the Earth's surface, it spreads out horizontally at high speed, creating an area of immense, localized wind shear. The speed of the air in the core of a severe microburst can exceed 150 miles per hour, rivaling the wind speed of an EF2 tornado. But the danger lies in its sudden, deceptive nature. For those on the ground, a microburst might feel like a sudden, violent blast of wind and rain, often powerful enough to flatten large stands of trees in a circular or starburst pattern, emanating from the point of impact. This specific damage pattern is what differentiates microburst damage from the convergent, rotational damage of a tornado. But for an airplane, particularly one taking off or landing, the danger is far greater and less visible. As a plane flies into a microburst, it first encounters a powerful headwind on the leading edge of the downdraft, which temporarily increases its airspeed and lifts a deceptively positive signal. But an instant later, the plane passes into the core of the downdraft, which dramatically pushes the plane down toward the earth. This is immediately followed by a powerful tailwind on the far side of the downdraft, which drastically reduces its airspeed and destroys lift. This rapid sequence lift gain downforce. Lift loss can force a plane to the ground faster than a pilot can react or compensate. Especially at low altitudes, microbursts are short-lived, sometimes lasting only minutes. But their sudden, immense power makes them one of the atmosphere's most insidious, invisible threats, demonstrating that fury can be unleashed not just in rotation, but in sudden, catastrophic blasts of descending air. Moving from the localized to the gigantic, we arrive at the true engines of weather chaos and some of the most complex, long-lived structures in the atmosphere, supercell storms. Most thunderstorms are relatively small, transient affairs, lasting less than an hour before exhausting their fuel. A supercell, however, is a different class of storm, a massive, organized, self-sustaining system characterized by a deep, persistent, and rotating updraft known as a mesocyclone. This rotation is the key to its longevity and destructive power, allowing the storm to separate its updraft from its downdraft, preventing the cooling rain from choking its own energy source. On satellite images and weather radar, these storms are colossal, sometimes stretching across hundreds of miles, larger than entire U.S. states. Within their towering cloud structure, which can pierce 10 miles, 16 kilometers up into the stratosphere, an entire complex weather system is born. They are the primary atmospheric incubators for giant hail, as we discussed with the hailstone's rings, intense lightning, and, crucially, the majority of the world's most violent tornadoes. The rotation of the mesocyclone provides the necessary spin to tighten and intensify the vortexes that become tornadoes. To watch one form from a distance is to see the atmosphere flex its muscles, a dark, rolling, majestic wall of cloud so vast it swallows the horizon. They are storms that seem alive, breathing, rotating, and growing, constantly feeding on warm, moist air and ensuring that the land beneath them feels utterly small and insignificant. Yet, even these dangerous systems are fundamentally part of the water cycle, transporting massive amounts of latent heat energy poleward and dumping the rain that sustains ecosystems, proving that the most life-giving force on Earth must occasionally manifest in profound violence. The sheer staying power of the atmosphere's anger is a further surprise. We typically think of thunderstorms as fleeting events, a burst of rain and noise quickly followed by clear skies. Yet, under the right conditions, these systems can endure far longer, forming vast, cohesive structures that defy the typical rapid decay of individual storm cells. These structures are known as mesoscale convective complexes, MCCs. An MCC is a sprawling, immense cluster of thunderstorms that can persist for 12 hours or more, traveling across entire regions and maintaining, or even increasing, their intensity throughout the night. The longevity of the MCC is its most remarkable feature. Within these vast complexes, individual storm cells rise, collapse, and regenerate in a continuous, self-sustaining cycle, constantly feeding on warm, moist air and releasing torrential amounts of rain. The key is their size. The complex is so large that the cooling effect of the rain from one cell acts to enhance the inflow of warm, buoyant air into other cells. This efficient internal atmospheric organization allows the system to remain active long after the sun sets, a time when most single-cell storms die out due to the loss of solar heating at the surface. These long-lived thunderstorms are often responsible for widespread flash flooding and prolonged periods of dangerous lightning and straight-line winds, particularly across the American Midwest and Great Plains. For those beneath them, the MCC becomes an unrelenting companion through the darkness, a never-ending chorus of rumbles, repeated flashes, and relentless rain. They remind us that weather is not always a brief, energetic event. Sometimes, the sky itself settles in for a long, restless stay, relentlessly cycling energy and moisture. And finally, we arrive at an extreme that is truly beyond the bounds of ordinary experience, a weather event that has lasted for centuries, a phenomenon of unparalleled electrical consistency. Over the mouth of the Catatumbo River in Venezuela, where it empties into Lake Maracaibo, a storm has been raging for as long as written human history has observed it. Known as the Catatumbo lightning or the everlasting storm, it is a unique natural phenomenon where lightning flashes occur almost nightly, sometimes for up to 10 hours at a time, for more than 200 nights each year. The geography provides the perfect, unique recipe: warm, immensely moist air rising off the shallow. Tropical Lake Maracaibo clashes violently with cold, dense air sweeping down from the surrounding high peaks of the Andes Mountains and the Perija Mountains. This constant, forceful collision creates a highly localized, intense electrical potential. The methane gas bubbling up from the massive oil fields beneath the lake is also believed to contribute to the ionization and electrical conductivity, further intensifying the atmospheric charge separation. From miles away, the sky above the lake glows with a flickering, silent display, often visible even to sailors far out at sea, who have long called it Maracaibo Lighthouse, because the storm is so vast and often so distant. The flashes are frequently seen, but the thunder is not heard, a light show of pure, silent power. Scientists are still studying the exact mechanisms that make this location so uniquely storm-prone. But one thing is certain: nowhere else on Earth does lightning pulse with such relentless, timeless rhythm. It is a constant, electrifying reminder of the planet's boundless, cyclical energy, a beacon of atmospheric power that is the perfect image to close this chapter, an eternal natural lighthouse. We turn now from the sound of ceaseless electrical energy to the phenomenon of absolute quiet, the profound, unique silence that descends upon the world during and immediately after a heavy snowfall. This effect is so distinct that cultures across the world recognize the silent sound of snow as a unique and deeply peaceful experience. This silence is not mystical. It is a direct consequence of the unique physical structure of fresh snow, turning the landscape into the world's largest, most efficient acoustic absorber. The key to this sound dampening effect lies in the way snow crystals stack upon one another. When snow first falls, it creates an immense layer of trapped air within and between the intricate branched crystals. This freshly fallen snow is incredibly light and fluffy, sometimes composed of over 90% air. This air-rich structure is an acoustic engineer's dream. It is highly porous. When sound waves, which are, after all, simply vibrations in the air, strike the snow's surface, they do not bounce back, reflect easily. Instead, they penetrate the highly irregular and porous surface and are forced to travel through the maze of tiny air pockets. As the sound waves travel through this labyrinthine structure, the energy of the wave is not just absorbed, it is dissipated and converted into tiny amounts of heat through friction. The vast network of interconnected air cavities acts as an incredibly effective noise trap, muffling and absorbing ambient sounds, particularly the sharp, higher frequency noises of traffic, voices, and machinery. This is why the silence of a snowstorm feels so complete and profound. The usual background hum of civilization is quite literally being swallowed by the soft, white blanket. However, this peaceful silence is temporary, and its duration is also a lesson in the physics of transformation. As the snow ages, or if the temperature rises above freezing, the intricate structure begins to change. The delicate, branched crystals settle, compact, and eventually melt and refreeze. This process of sintering reduces the amount of trapped air and makes the snow surface harder and denser. When this happens, when the snow becomes old, icy, or hard-packed, it loses its porous, sound-absorbing quality and begins to behave more like a solid, reflecting sound waves instead of absorbing them. This is why, paradoxically, sounds often seem sharper and travel farther over hard-packed or icy snow than they do over fresh powder. The quietest time is the moment the fresh snow stops falling, before the sun or compaction can ruin the acoustic dampening properties of the frozen crystals. This quiet observation of the world being muffled by snow allows us to reflect on the nature of atmospheric transformation and the physics of sound itself. The storm does not just bring a visible change of landscape, it brings a profound auditory change, proving that stillness in nature is often an active state a consequence of billions of tiny crystals working together to absorb the noise of the world. We now turn our attention from the ground and the immediate atmosphere to the immense, radiant dome above us, asking a question that is fundamental yet often overlooked. Why is the sky blue? This is one of the oldest scientific queries, and its answer reveals a beautiful and surprisingly gentle form of atmospheric physics that makes the color of our world a constant, vast optical illusion. The light that reaches us from the sun appears white, but it is actually composed of all the colors of the visible spectrum, the same colors we see when light is bent through a prism or reflected off a raindrop to form a rainbow. Each of these colors has a different wavelength, ranging from the longer, less energetic red light to the shorter, more energetic violet and blue light. The sky is blue because of a phenomenon called Rayleigh scattering, named after the British physicist Lord Rayleigh. As sunlight enters Earth's atmosphere, it collides with the dense curtain of gas molecules, primarily nitrogen, text dual R, and oxygen, text O2 that surrounds our planet. These molecules are far smaller than the wavelengths of visible light. Lord Rayleigh discovered that these tiny atmospheric molecules are far more effective at scattering the shorter, bluer wavelengths of light than they are at scattering the longer, redder wavelengths. Think of the air molecules as tiny obstacles. They violently deflect the fast, short blue light in all directions across the sky. When you look away from the sun, the blue light scattered toward your eye from every direction makes the entire sky appear blue. Conversely, the longer, less scattered red and yellow wavelengths of light continue their straight path, passing mostly unimpeded through the atmosphere until they hit the ground. The paradox here is that the sky is not blue because of blue light alone. It is actually a blend of blue and violet light. Violet light has an even shorter wavelength than blue and should, technically, be scattered the most powerfully. However, two crucial factors make us perceive the sky as blue. Not violet first. The sun's output contains slightly less violet light than blue light. And second, our human eyes are significantly less sensitive to the violet end of the spectrum. Our cones, the color receptors in our eyes, register the strong blend of blue and violet as a brilliant blue. If our eyes were built differently, the sky might be a deep, dark violet. This principle of scattering also explains one of the most beautiful and restful sights in nature, the sunset. As the sun drops toward the horizon, its light must travel through an increasingly long and thick column of atmosphere to reach your eyes. By the time the light has passed through this immense atmospheric curtain, nearly all of the short wavelength blue light has been scattered away, leaving only the long wavelength colors red, orange, and yellow to pass directly through. These remaining colors paint the clouds and the lower atmosphere in the fiery, warm tones we associate with the end of the day. So, the blue sky is a vast, peaceful optical illusion, a consequence of light being gently and consistently diffused by the very air we breathe, a constant reminder of the elegant physics governing our visual worlds. We delve now into two fascinating atmospheric events that manipulate our senses of sight and sound: the thermal inversion and the fog bow. Both are subtle, common occurrences that dramatically bend the known rules of physics in our lower atmosphere. We are used to the simple rule that air temperature decreases with altitude. This is logical. The ground is warmed by the sun and re-radiates heat, so the air closest to it is warmest, and the air cools as it rises. A thermal inversion, however, is a profound disruption of this rule. It is a meteorological phenomenon where a layer of warm air settles above a layer of much colder air near the surface. The temperature profile is literally inverted. This inversion layer is highly significant because it creates a lid on the atmosphere. The cold, dense air near the ground cannot rise through the warm, less dense air above it, and thus, vertical mixing of the air almost completely ceases. The results of this atmospheric cap are profound and directly impact our quality of life and perception. First, an inversion can trap pollution near the ground. Any vehicle exhaust, industrial emissions, or smoke released into the cold air layer cannot escape upward, leading to a dangerous concentration of smog and particulates, especially in large urban basins surrounded by mountains like Los Angeles or Mexico City. Second, and more peacefully for our purpose, an inversion can dramatically muffle or amplify sound in strange ways. Sound waves traveling through the atmosphere are sensitive to temperature gradients. When sound waves travel through an inversion, they are often refracted or bent downward toward the ground. This bending can make distant sounds, such as a train whistle, the roar of the ocean, or even distant conversations, seem to travel vast distances with startling clarity, defying the typical rule that sound dissipates with distance. Conversely, sometimes the inversion simply traps and muffles all sounds within the cold layer, contributing to the unsettling silence often noted during extreme cold snaps. The thermal inversion is a silent, invisible force that temporarily re-engineers the local atmosphere, changing the dynamics of heat, pollution, and sound. We move now to a phenomenon related to the rain and fog. We have already discussed the fog bow. You know the familiar rainbow, a beautiful, vibrant arc of color created when sunlight passes through the liquid raindrops, refracting, reflecting, and separating the light spectrum. A fog bow is created by the same optical principles, but with a critical difference in the size of the water droplets. A fog bow is formed by the sunlight passing through the tiny, microscopic droplets that make up fog or mist. Since these droplets are far smaller than raindrops, often less than 0.5 text and micron in diameter, the light passing through them undergoes a greater degree of diffraction, spreading out than simple reflection and refraction. This diffraction effect smears the colors. Instead of seeing the vibrant bands of red, orange, yellow, and blue, the observer sees a much paler, broader arc, a beautiful, ghostly white or gray arch against the fog. It is often described as an arc of light rather than an arc of color. Because the droplets are so small, the light interference effects overpower the color separation, leaving only a faint, luminous outline. They can be particularly stunning when viewed from a high vantage point. Looking down onto a fog bank, the fog bow is a perfect, ethereal reminder that the precise size and nature of the water molecules suspended in the air determine the visual language of the sky. The gentle, silent white arc of the fog bow is the rainbow simplified, softened, and absorbed by the surrounding mist, a perfect image of calm, diffused light. We return momentarily to the world of ice and the sheer physics of precipitation, focusing on a truly extreme measure of atmospheric power, the terminal velocity of the world's largest hailstones. While we previously discussed the structure of hail layers, let's consider the speed and force with which these icy diaries arrive. The terminal velocity of any falling object is the maximum speed it can attain, reached when the force of air resistance pushing up equals the force of gravity pulling down. For the most colossal hailstones, this speed is nothing short of incredible. Recall the record-breaking hailstone from Vivian, South Dakota 2010, which weighed nearly 2 text pounds and measured 8 text inches across. Because of its massive size and weight, its low surface area to mass ratio, it cuts through the air with terrifying efficiency. Scientists estimate that a hailstone of that magnitude would have reached a terminal velocity of well over 100 text miles per hour, $160 text km upon impact. This is the speed of a car on a highway, or a pitch in Major League Baseball. It is a terrifying testament to the power of gravity working on a substantial mass forged high in the violent updrafts of a supercell. The kinetic energy released by a 2-pound projectile hitting the ground at 100 text ambarasar is enough to cause severe structural damage to homes, cars, and, tragically, any living thing caught outside. This is why a simple hailstorm, when extreme, is one of the most violent manifestations of gravity and air resistance in the atmosphere. From the force of falling ice, we ascend to view a cloud formation that is perhaps the most bizarre and beautiful visual expression of instability. Mementus clouds. While most clouds feature flat, or upward bulging bottoms as air rises and condenses. Mammatus clouds are characterized by stunning, inverted, pouch-like, or lobe-shaped formations hanging from the base of a cloud. Their name comes from the Latin mamma, meaning udder or breast. These formations are often observed on the underside of a cumulonimbus anvil cloud, typically after the most severe part of a thunderstorm has passed. For centuries, they were viewed with alarm because their appearance was often linked to severe turbulence and potential hail. The scientific reason for their strange, hanging shape is a fascinating reversal of typical cloud dynamics, involving sinking, moist air. Mammatus clouds form due to a process called negative buoyancy. Unlike most clouds, which form as warm, buoyant air rises and cools. Mammatus clouds are thought to be caused by cold, moisture-laden air sinking into a warmer, drier layer below. As this cold, saturated air sinks, the moisture droplets at the bottom of the cloud evaporate back into the warmer, drier air. This evaporation causes the air to cool further, making it denser and accelerating its descent in the localized pouches. The result is an unstable, dynamic equilibrium. The sinking, colder air creates the distinct, sagging lobes. The visual effect, particularly when illuminated by the low light of a setting sun, which highlights the curvature of each individual lobe with deep, dramatic shadows, is breathtaking. It transforms the normally flat base of the cloud into a rippling ceiling of pouches, often glowing in vivid reds, oranges, and pinks. The mammatus cloud is a perfect, strange example of atmospheric dynamics working in reverse, turning the powerful storm's aftermath into an enormous, silent canvas of suspended, inverted beauty. It is the visual equivalent of an auditory echo, a final, spectacular flourish before the storm is truly gone. We now journey to the quiet, slow motion world of deep ice, where the atmosphere's work is recorded not by falling flakes, but by structures that last for millennia. Glacial ice, particularly the vast sheets covering Greenland and Antarctica, represents an immense, slow-motion reservoir of past weather. The ice in these sheets has a unique, crystalline structure, containing layers of trapped air and dust, a silent physical record of Earth's ancient atmosphere. When scientists extract ice cores from these glaciers, they are retrieving a frozen chronology. Each layer corresponds to a specific year's snowfall, compacted by the weight of successive years. By analyzing the air bubbles trapped deep within the ancient ice, some dating back hundreds of thousands of years, scientists can directly measure the historical composition of the atmosphere, including levels of carbon dioxide, methane, and other gases that governed the climate long ago. The deep ice, therefore, is not just frozen water. It is a silent, geological diary of the atmosphere's history, preserving the air of the past in tiny, pressurized pockets. Furthermore, by analyzing the oxygen isotope ratios within the water molecules of the ice specifically, the ratio of oxygen 18 to oxygen 16, scientists can determine the temperature and broader climate conditions at the time the snow originally fell. These heavy to light oxygen ratios change reliably with temperature, allowing researchers to reconstruct historical climate changes, documenting ice ages, warm periods, and periods of rapid transition. This silent, meticulous work of ice serves as a powerful reminder that the weather of today is directly influenced by the long-term, slow-moving cycles of the past, recorded in the planet's vast, frozen libraries. We conclude our exploration of global weather cycles with one of the most significant, yet least known, large-scale phenomena, the atmospheric river. You have likely heard of the effects of these systems: massive rainfall and flooding on the west coast of North America and other coastal regions. But the concept itself is vital to understanding the global water cycle. An atmospheric river is a long, narrow corridor of concentrated moisture that travels through the atmosphere, much like a river in the sky. These features are generally about 40 to 60 times wider than the Amazon River and can carry a moisture volume equivalent to the average flow of the Mississippi River through a given cross-section. They are immense, transient pipelines of tropical moisture. When these vast pipelines of vapor encounter a major land barrier, such as the mountain ranges along a coast, the air is forced to rise. This rapid lifting causes the air to cool, leading to massive, intense condensation and the eventual release of torrential rain and snow over a very short period, while providing essential water and snowpack for agriculture and urban use, with a few of these events often supplying a large percentage of a region's annual precipitation. They can also cause catastrophic flooding and landslides due to the sheer volume of water delivered so quickly. The atmospheric river is a beautiful, invisible example of the atmosphere's large-scale transport system, a crucial mechanism that connects the warm, moist tropics to the cooler, drier mid-latitudes, and a final, humbling image of the sky's power to carry and release immense, life-altering quantities of water. We arrive at our final reflection, drawing together the paradoxical truths we've uncovered about the atmosphere, its immense weight held aloft by tiny air currents, its profound, destructive power contained in millimeter-sized hail, and its visible beauty dictated by invisible molecular physics. Our closing thoughts center on the silent harmony that results from these violent, ceaseless cycles. Consider the concept of atmospheric pressure. We live and breathe at the bottom of an ocean of air, and that air exerts a tremendous force on us, often without notice. At sea level, the weight of the entire column of air above a person presses down with a force of approximately 14.7 pounds per square inch psi, or about 101.3 kilopascals. This means that the total weight of the atmosphere pressing down on the average human body is equivalent to the weight of a school bus, thousands of pounds of force. Yet, we don't feel crushed. This is the final, beautiful equilibrium. The fluids and air inside our bodies exert an outward pressure that perfectly counterbalances the immense inward pressure of the atmosphere. We are not crushed because we are in perfect, silent harmony with the weight of the sky. This balance is a constant, subtle contract between our biology and our environment. Any rapid change in external pressure, such as in a fast-climbing airplane or a deep-diving submarine, is immediately and uncomfortably felt, proving just how finely tuned our equilibrium is. The ability to exist comfortably under this crushing, invisible weight is a testament to the planet's perfect design for life. As the quiet pulses of the Catatumbo lightning fade into the distance, and the final image of the balanced pressure settles upon your mind, allow your thoughts to drift away, taking comfort in the vastness, power, and ultimate predictability of the atmosphere's great cycles. From the invisible weight of the air we breathe to the silence of the hoarfrost and the light of the distant blue sky, the world of weather holds both immense power and profound peace. The atmosphere, in all its complexity, is ultimately a system of balanced forces, always seeking equilibrium, always returning to calm. In the science of the sky, we find the perfect metaphor for rest. The heaviest burdens are supported by the smallest movements, and the greatest chaos is contained within a predictable, elegant system. If you've enjoyed this gentle journey into the science and stillness of the sky, please check out the other deep sleep stories on the playlist displayed on your screen. You'll find more explorations of the quiet wonders of our world, all crafted for a perfect night's rest on the Sleep Drift Stories channel. Like, share, and subscribe to help others find their way here, one sleepy soul at a time. Thank you for joining us tonight on this journey through the sky's hidden wonders. We hope the thought of floating clouds, the gentle pressure of the air, and the silent rhythm of the weather brings you deep calm and restorative rest. Good night and sweet dreams.